Hey guys, welcome to Physics 390 class 23. This class is on scattering and partial waves. And we'll be talking about scattering, which is when one object or a beam is impacted and goes off in different directions from another. And partial waves will be a technique that's used when we treat the scattering according to quantum mechanics to find the results of the scattering. So this comes from chapters 10.1 to 10.2 of the textbook. Okay, let's take a look at scattering and partial waves. So we'll start off with classical scattering theory before we get into quantum. And so for classical scattering, we have a scattering center, which is the center of the object that we're sort of throwing stuff at or sending a beam into. And something comes in here from the left and is scattered, so is deflected by the either direct impact with or a force coming from the scattering center. So it's deviated from its straight line trajectory. The goal in classical scattering theory is to find the scattering angle theta, which is the angle measured from the scattering center tangent to the final trajectory of the scattered object as it continues here, as a function of what we call the impact parameter B. The impact parameter is the if the incoming object continued straight on its trajectory, it's the distance it would pass from the scattering center. So it's the perpendicular distance to the scattering center of the incoming object. Okay, so we'd like to find the scattering angle as a function of the impact parameter B. Generally, theta, the scattering angle, increases as B decreases. So the closer we get, the smaller B gets, the closer we get to the scattering center, the stronger the scattering will get, and the more the particle will be deflected. As we get further out here, if B gets greater, increases, theta will not be as great because it doesn't feel the scattering center as much. Okay, so our goal in classical scattering theory is to find the scattering angle theta as a function of the impact parameter B. So why might we want to do that? Well, one of the key quantities which we look at in scattering is called the differential cross-section, D for differential, which is a function of theta, the angle, the scattering angle. And the differential cross-section is a proportionality factor between the outgoing solid angle and the incoming cross-sectional area. So this diagram should hopefully help with that. So here is an outgoing solid angle. Okay, so a solid angle in terms of variables would be sine of theta d theta d phi. So it's the volume element in spherical coordinates without the r squared. That's what a solid angle is. Anyway, it's basically a two-dimensional patch of angle. So if we look at a given scattering angle theta, as we increase the size of the solid angle, we expect more and more of the incoming particles or things being scattered to go through this. So there's a proportionality here that the bigger the area we take here, the bigger the solid angle here, the bigger a portion of the incoming cross-sectional area of the beam must be feeding into that solid angle in order to produce that increasing amount of outgoing stuff. Okay, and this proportionality factor between the solid angle and the cross-sectional area is called the differential cross-section D, and it depends on theta. So as we move out in theta, this proportionality constant will change. It generally doesn't depend on this angle phi, because most scatterers are have symmetry around the axis, symmetry around this axis, and so the phi, there's no phi dependence in D. Okay, so that's the differential cross section. It's this proportionality factor. Now, you can argue that, and it's argued in the text. We won't produce the full argument here, that the differential cross section D of theta can be related to how B depends on theta. Okay, so it turns out to be B over sine theta, dB d theta, absolute value. So why is it the absolute value? Well, we said that as theta increases, B decreases. So this derivative would be generally negative. So we need to take the absolute value to get a positive value for D, which it should be positive since it's a proportionality factor between two positive numbers. Okay, so it sort of makes sense that that the differential cross section should be able to be related to how B depends on this angle, or how this angle depends on B. Conversely, this is the same for the derivative. Okay, so the next thing we can look at is the total cross section, which is the total area of the incident beam, which is scattered by the target. Okay, so it's the total amount of area of the beam which is impacted by the target as it passes by the target, how much of it is actually deflected. And we can get that by integrating, and we call that sigma, the cross section sigma, by integrating d sigma. But d sigma is d theta d omega. So we integrate over all angles d theta of d omega, and we get the total cross section, the total amount of area of the incoming beam which is deflected by some amount by the scatterer, the scattering center. Okay, and it turns out, just to take a definite example, for a hard sphere scatterer, so just like picture a little marble and you shooting little pellets at it, we find that the total cross section turns out to be the differential cross section, which turns out to be r squared over 4 times the integral over all solid angle, which is 4 pi. So 4 pi times r squared over 4 gives pi r squared. And that kind of makes sense, because if you think about it, if you think about the marble and you look straight at it, the area that it presents is equal to pi r squared. So that's the area that of an incoming spray of particles that would actually be deflected, because they would actually hit it if it was in its path. And the cross section it presents to an incoming path is equal to its pi r squared, the area of a great circle on the marble. Okay, one more thing about classical scattering theory. There's an alternate expression for the differential scattering cross section, which can be written as 1 over L times dn over d omega, where omega is a solid angle. So this one is motivated by measurements in experiment. In experiment, you might take a little detector which took up a little bit of solid angle. You would measure an event rate, which would be the number of particles or scatterers per unit time in that solid angle. And then to get the differential cross section, you have to normalize that by the beam intensity, because it makes sense. If you doubled or tripled the beam intensity, you would double or triple the event rate. So you normalize the event rate by the beam intensity, which is the number of incoming things being scattered per unit area per unit time. Okay, so that's classical scattering theory. So we've introduced the scattering angle, the impact parameter, the differential cross section, and the total cross section. And all of those will carry over into the quantum, which we'll look at now. So quantum scattering theory, as you can expect, might be a little bit different. Rather than a beam of particles coming in and hitting off of a center, we represent the incoming thing to be scattered by an incident plane wave, e to the I k z, where the z-axis moves to the right, points to the right here. And then the stuff coming out, or the scattered part, is an outgoing spherical wave, which would be e to the I k r, so radially coming out from the origin here. And the wave function, which would include both the incoming wave and the outgoing spherical wave, would be some constant times e to the I k z, the incoming plane wave, plus e to the I k r. Now over r, this division by r is made so that to make the flow of probability in from the e to the I k z match the flow of probability out from the e to the I k r. If this r weren't there, we would get more probability density flowing out than would flow in. So we have to divide by r here. And notice also there's an angular factor here built in. So that's the scattering angle, which we talked about before. So as the intensity of the spherical wave depends on theta, the theta with respect to the z-axis. Okay, so it turns out this scattering amplitude, this factor here, this f of theta, which multiplies the spherical wave, it's what's called the scattering amplitude, is related very closely to the differential cross-section, as would be measured in an experiment. We can show, we won't go through all the arguments here, that d of theta, the differential cross-section, is just the square modulus of the scattering amplitude. So if we can find the scattering amplitude by solving the quantum problem, we immediately have the differential cross-section that's predicted in space, in experiment rather. Okay, and so how do we find this scattering amplitude? Well, it's usually calculated with one of two techniques. One is partial wave analysis. The second is the Born approximation. And we're going to look in just now at partial wave analysis and how that might work. Okay, so remember, our goal is to find the scattering amplitude f of theta, and from that to find the differential cross-section and the total cross-section. Okay, so partial wave analysis. Well, let's take a step back for a second and think about trying to solve this quantum problem. The radial equation for a central potential, we'll assume we have a central potential. It just depends on the distance r from the scattering center. This is the radial equation which we looked at, for example, in the hydrogen atom. This was the radial equation. It has a kinetic energy term, the scattering potential, a centrifugal term, and then is equal to the energy times the wave function, basically. So at very large r, okay, so at very large r, v of r is going to become negligible, because v of r is only, can't extend forever. It has to drop off. At very large r, its influence will drop off. The centrifugal term here will also drop off because it goes as 1 over r squared. So as r gets very large, both v of r and the centrifugal term are negligible. So this expression here, this whole thing, this drops out, and we get the second derivative of u with respect to r is minus 2me over h bar squared u, but we call 2me over h bar squared k squared. So we get that d squared u over dr squared is approximately equal to, since we're neglecting this as an approximation, minus k squared u. So the solution to this is a sinusoidal, because it's a minus k squared u. And so we get an outgoing spherical wave, u, is some constant times e to the I k r. That would solve this if you plug that into this this approximate differential equation here, this u would solve it. But remember that u is actually equal to the r coordinate times the actual radial wave function. So the actual radial wave function would be u divided by r, or proportional to e to the I kr over r, which is what we saw before, based on the argument that the outgoing spherical wave should conserve the probability coming in and coming out. Okay, so we can take a look here. We've just been looking in what we call the radiation zone, which is out here where outside of this intermediate region. In the intermediate region, the centrifugal term still holds some sway and holds some influence. In the scattering region, but we assume the potential in the intermediate region can be taken to be zero. Meanwhile, in the scattering region here, both the centrifugal term and the potential term are important. So we have both terms important here. We have just the scattering term important here, and outside here, neither term is important. And out in this radiation zone, we get this e to the I kr over r. Okay, but what about in this intermediate region? What do we get there? So if we assume v of r is localized, then as we were just mentioning, in the intermediate region, we can ignore v of r. So we can ignore v, but not the centrifugal term. And it turns out the desired solutions in this intermediate region, taking into account the form of the centrifugal term, which is active there, are called spherical Hankel functions of the first kind. Okay, so we're not going to study those in depth, but they're written as lowercase h for Hankel, sub L because they have an index L, which has to do with angular momentum. And then the one here indicates of the first kind. And they're a function of kr, because kr is what the outgoing spherical wave was a function of. And it turns out that as kr gets much bigger than 1, so as we move out further out from the intermediate region out into the radiation zone, the spherical Hankel functions have an go as or limit to the behavior e to the I kr over r. So they match what we would expect if they're the solution in the intermediate region. If we go out to the radiation zone, they match what we found from the approximation in the radiation zone. So this matching indicates that they're the proper function to use these spherical Hankel functions of the first kind in this intermediate region. Okay, so the full solution in the intermediate region can be written like this. Psi of r, theta, and phi is a times e to the I kz, that's the incoming plane wave. And then this is the outgoing spherical wave. It's got spherical harmonics. It's got radially, it has the spherical Hankel functions. And then there's a coefficient here for each L and M of the spherical harmonics and the radial and the L for the Hankel function. Okay, so this is the very general solution. But as long as we have a central potential, we have spherical symmetry. And if we have spherical symmetry, then the answer for our psi cannot depend on phi. And if it can't depend on phi, then m must be 0, because m for m not equal to 0 has a phi dependence. So we can't have a phi dependence here. So we can restrict this sum to just m equals 0. And this allows the full solution, this solution here, to be rewritten in the form phi of just r and theta of ae to the I kz plus, and we choose to rewrite this constant here as, instead of just c, we write it as ki to the l plus 1 times 2l plus 1 times al. And then this PL cosine theta is the theta part of the YLM without the phi dependence. So that's what's happening here. Okay, and the reason we do this change in the behavior of the constants is just to have the expressions we have in terms of this quantity AL, which we'll name in a second, have a convenient form. Okay, so and this term AL is called the Elf partial wave amplitude. It's a partial wave because there's clearly an infinite sum of waves which come out, and they all form part of the solution, and they're associated with angular momenta. So the ELF partial wave has angular momentum associated with angular momentum quantum number L. Okay, so that's what the partial waves are. They are when they're weighted by the partial wave amplitudes, and the radially they have the Hankel function, spherical Hankel function of the first kind, as their radial dependence. Okay, so moving along to the partial wave analysis. So from this expression, which we just wrote, we just were looking at on the previous slide, AE to the IKZ plus K times these constant times our partial wave amplitude times the spherical Hankel function times our basically our Legendre polynomial, which is the part of the spherical harmonic. So from that expression and the large R behavior of spherical Hankel functions of the first kind, we can actually deduce what the if we have this solution here, if we know what the ALs are, we know what the partial wave amplitudes are, we can deduce by doing a limiting behavior of this at large R, what the scattering amplitude would be in terms of the ALs. And it turns out to be this sum of 2L plus 1 AL PL cosine theta, which is a very nice expression. And that's the reason why why the people who originated this derivation and approach rewrote this constant in the way they did. So they would get this kind of very compact expression for the scattering amplitude. So this relates the scattering amplitude F of theta to the partial wave amplitudes AL. And then remember, our goal was to find the partial wave amplitude, the scattering amplitude F of theta. But once we have F of theta, we can also find the differential cross-section, which is the scattering amplitude squared. So here, with this sum as the scattering amplitude, we would have the square of a sum. So we would get this double sum here. So it would look something like this. When we integrate this over angle, some nice simplification occurs. When we integrate the differential cross-section over the solid angle, remember we get the total cross-section sigma. And that total cross-section sigma just turns out to be 4 pi times the sum over L, 2L plus 1 AL squared. So a really nice expression here, which also justifies this kind of fiddling with constants, which was done before. Okay, so how do we find these AL? They seem to be the key to finding the scattering amplitude F theta, and then the differential cross-section, which we can compare to experiment, and the total cross-section, which we can compare to experiment. So to find the AL, we match solutions in the scattering region, the very inner region where the potential is active, to solutions in the intermediate region via boundary conditions. So at that boundary between the inner region and the intermediate region, we require that the solutions we get match. And to help in doing this, we use something called Raleigh's formula. So before, notice that we had psi of R and theta, but we had Z appearing here. So whereas here we had R and theta in this second term. So we'd like to have psi all in terms of r and theta. And we can do that by using what the physicist Lord Rayleigh was able to establish, that e to the ikz, the plane wave, can be written as a sum over these polynomials, Legendre polynomials, and these are what are called spherical Bessel functions. So there's this sum here, which expresses e to the ikz in terms of r and theta. So we can rewrite this expression up here now fully in terms of r and theta. Okay, so we're just replacing e to the ikz with this expression here. So we have an a still on in front. We factor out I to the L times 2L plus 1 and a PL cosine theta. We're left with JL of KR here. And then left here, since this was I to the L, this was I to the L plus 1, we have an I times a K times the AL, the partial wave amplitude, times the Hankel function of the first kind. Okay, but the important part here is that we now have the solution in the intermediate region fully in terms of r and theta. So we can match boundary conditions with what we get in the inner scattering region. And from that, by matching the boundary conditions, we can determine with some work for more complicated potentials what the AL, these partial wave amplitudes are. So let's conclude by looking at one case which we looked at before for classical scattering, which is hard sphere scattering. So suppose we just had a hard sphere, what would quantum scattering tell us about that? Well, the boundary condition would be that the wave function at the radius of the sphere, which we'll call A here, at any angle should be equal to 0. Because if it's a hard sphere, the incoming plane wave can't penetrate the hard sphere, because the hard sphere means the potential goes to infinity. So at the edges of the sphere, at the edges of the sphere, we have the wave function being 0. So this means that this, to match that boundary condition, this intermediate region must be 0. And the only way it can be 0 is if this term in brackets is 0. For that term in brackets to be 0, we can say that the partial wave amplitude AL is equal to I times JL KA over K HL1 of KA. So if we plug that in at R equals A, we plug this in here, we get, let's see, the I times I gives a minus sign, the K's cancel, the J over H gives us a J here. So we're just left with JL KA minus JL KA, or 0. So it matches. And then by using the properties of JL and HL, we can actually write the total cross-section in a sort of a nice or a useful form. It's not terribly pretty, but it's useful, as we'll see in a second. It turns out to be using the properties of both these functions. 4 pi over k squared sum over L, 1 over 2L plus 1 times this factorial combination times Ka to the 4L plus 2. Okay, so this is most useful if we look at low energy scattering. So for low energy scattering, K is going to be a small number because K is directly related to the energy. So Ka will be much less than 1. If Ka is much less than 1, then the higher powers here for L equal 1, say, so L equals 0 gives a power of 2 to Ka. L equals 1 gives a power of 6. So if Ka is small, Ka to the 6 will be super small. So we can ignore all L's above L equals 0. So if we look at that, if we just take L equals 0, we have 1 over 2 times 0 plus 1, or 1 over 1. 2 to the 0 is 0. 0 factorial is 1. 2 to the 0 is 1, rather. 0 factorial is 1. 2, 0 factorial is 1 here. And then we have Ka times Ka squared, because L equals 0. So we have basically 4 pi over K squared times K squared A squared, or 4 pi, the K squareds cancel, we get 4 pi A squared. So the total cross section here for low energy scattering is 4 pi A squared. This is actually 4 times the classical result. You remember in the classical result, when we were talking about the marble, that the scattering cross section was total scattering cross section was just the area of a circle with the radius of the marble. In this case, it was pi r squared before, it would be pi a squared here. But here it's 4 pi a squared, which is the total surface area of the marble. So it's 4 times the classical result. And this is kind of because this wave sort of diffracts around the hard sphere, and it kind of probes and feels the entire surface area as it scatters. So that's an interesting quantum prediction, which is borne out in experiments of where quantum scattering is necessary. Okay, so just for a quick summary, we've looked at scattering and partial waves analysis. We looked at classical scattering. We looked at the impact parameter and the scattering angle and the relationship between those two. How those could be, the relationship with those two could be used to calculate the differential cross section, which relates the outgoing solid angle to the incoming area of the beam. And then we looked at quantum scattering, where we looked at a partial wave, or excuse me, a plane wave and an outgoing spherical wave. And then we defined the scattering amplitude as the angular dependence of that outgoing spherical wave. And then to find that that scattering amplitude, we instituted partial wave analysis, which involved these partial wave amplitudes AL. And once we have the AL, we have a very nice expression which gives us the scattering amplitudes. And from the scattering amplitudes, we can get the experimentally observed differential cross-section and the total cross-section. And we had an example here for hard sphere scattering, where the quantum result was 4 times the classical result. Okay, I hope that gives you some idea about scattering in the quantum regime, or the quantum scattering, and some of the terms used in classical and quantum scattering, and the technique of partial wave analysis. Thanks for your attention, and I'll see you in class.